Hello and welcome back to another video with It's Dr. Dan, and today we're going to be learning about VSEPR theory. So this is where we're going to be taking our Lewis structures. So if you saw my previous video on Lewis structures, we're going to be taking that and bringing it into the 3D world. Being that these different molecules that we're seeing, they're not just something that we write on paper, they exist in our everyday life, and being that we ourselves live in a three-dimensional world, so do they. So when we are looking at this, what is VSEPR? So if you're taking a chemistry class, you might have heard this concept, and this is about valence shell electron pair repulsion theory, or VSEPR for short. And why is it that we care about it? Well, the whole idea is to try to figure out what is the lowest energy configuration for a molecule, meaning when is it relaxed? So, for example, like whenever you're at home, when are you the most relaxed? Is it when you're playing games, reading a book, or doing, whatever you enjoy? Well, molecules are the same way. They like to have a point where they can be relaxed. So, what we're actually going to be trying to see is we're going to be looking at different electron groups. And what I mean by electron groups is it's everything that is attached to the central atom. So, whatever is in the middle, whatever can make the most friends, in that Lewis structure, they're going to be bound to all these atoms. But what's going to be happening is the atoms connected around the central point are going to be repelling each other like a magnet, or like in this GIF that I found here, right? So they're all going to be pushing each other away. Now, when they are doing that, they're trying to just spread as far apart as possible, but still be bound. So let's first just start by practicing counting electron groups. So I'm going to draw a couple Lewis structures, and we're going to be counting the number of groups. Now, keep in mind, groups can either be they can be lone pairs, bonds, anything around it is considered a group. So when I write that down, we're going to be counting lone pairs and bonded electrons. All right, so when we have those, so let's say if I take our first one, let's do what we're all breathing out all the time. So CO2. So if I have this particular molecule, how many electron groups do I have? Well, we are going to first see that we have our central atom, which is carbon, and we're going to be counting how many things are connected to it. So what we have is we have one oxygen on the right-hand side, and then we also have one oxygen on the left-hand side. So when we see that, we have one, two electron groups on this. So this one has two electron groups. Now, if we look at a different molecule, let's say if I pick ammonia. So if you've ever maybe cleaned, you might have used ammonia before. So if I want to draw this structure, we'd have nitrogen as our central atom. And then we want to count how many different groups are there around this. So some of them could be, if we have the hydrogens, each one of these is a group. So we have one, two, three different electron groups. But you can't forget, we also have to count the lone pairs because they are also their own unique group. So when we look at this, we have one, two, three, four groups all around that structure. If I were to draw one more, well, let's do formaldehyde. So I have CO with the double bond with two H's. We can once again try to highlight all of our different groups. So I have one for oxygen, and then I have one of the hydrogens on the left, and then one on the right. So how many electron groups do I have? Well, this is going to be a total of three electron groups. So I'll just fill all those out. So 3, 4, and 2 for all these different structures. And that's what we're looking for, is how many electron groups. So now how should we think about that? So when it comes to the different groups, what we are trying to do is think of them as bulky balloons. So meaning if you imagine having balloons in your hand, everybody's played with balloons at some point, and you were to hold them. Well, if you were to tie the two at the end at the bottom at the knot, well, what would happen? Well, they would bounce off each other and they would repel each other. So, and this is how we're going to be determining the different geometries behind them. So, if you think about a circle, which is a complete perfect shape. So, a circle, if I were to kind of draw that, what is the angle for how many degrees are in a circle? Wow, and that did not draw well. So, if I have a circle, how many degrees are there around it? Well, there are 360 degrees. So that's that perfect shape. So when we're adding groups, what we're doing is taking that 360 and simply dividing it by the number of groups to kind of figure out the general angle behind it. Now that's more, it represents more of a two-dimensional space though. It's once you start getting past 4, 5, 6 groups, it starts getting a little bit more intricate, a little bit more unique, trying to purely push them apart. So, if I have something that is two groups, well, what's the farthest they can be from each other? Well, think of it as if me and you were interacting with each other. If we're talking to each other right now in person, we're going to be face to face from each other. We're going to be 180 degrees apart. So what that's going to be is if I have my central atom right here in the middle, well, and I have that as a little knot that's being tied, if I have two balloons, the blue and the red on both sides, this is a linear geometry, so face to face. Now that angle would be 180 degrees. Now if we change that picture to, let's say, 3 electron groups, well, what's the most that they can be apart? So if I hold 3 balloons that are all far apart from each other, we can do that as well. So if I have my 3 balloons and I want to show all 3 of those, well, we can see that we have 1, 2, 3. A triangle would be that perfect shape showing that 120 degrees, or that trigonal planar is what this shape is called. We can do 4 groups. So if you think of tetra as 4, so in this one, it's more drawn similar to like a pyramid. So if we kind of think about the connecting all these different balloons via their corners, we can see that, oh, well, this is actually looking like geometric shapes and how they're all put together. So this one's tetrahedral, which has an angle of 109.5 degrees. Now, if you didn't notice, there's some weird symbols that are being shown here. So what do all these represent? So we have this bold line. This is a wedge. This is telling you that this balloon or this atom is coming out at you. So out of the screen and towards you. Where I have these dashes, they're going behind your monitor or behind your phone right now. So that's going away from you. So that's what these are showing. When we just have a regular line, this is representing that it's being drawn in the plane. So if you're like holding your device right now, for example, it's in line with that device. So it's in line with your screen or whatever it is that you are actually looking at. So we're drawing it in a 3-dimensional perspective. So well, now all these are all referring to just electron groups or just atoms being bound. What about lone pairs? What do they do? Well, the thing about lone pairs is that they are extremely repulsive, meaning it's a concentrated area of electrons. So they're going to want to push everything away from it. However, they're still attached. We still interact with them. We still have them around, but they're like the friend that, yes, you want to be friends with them, but you can only handle them in small doses. So, you'll talk to them for maybe an hour and then you'll step to the other side of the room. That's kind of what's happening here. So they're a little repulsive. So what happens is that these can change the geometry. So if we have our original tetrahedral geometry on the left here, well, if I decide to pop one of those balloons, well, what's going to happen is you're going to hear that loud bang and everything's going to shudder away from it. So if we pop one of them and we have our 2 lone pairs drawn here, they're going to be pushing the other all the different atoms away from it. So it's going to be pushing them downwards, constricting the angle. So the 109.5 for tetrahedral is going to become less than that, and they're going to all the different atoms are going to push together. So that'll be trigonal pyramidal. Now, when we add more lone pairs or even more repulsive, they're going to push even farther away from everything else. So that's going to become bent. Now, is this something that you have to memorize every single one of these? I hope not. I mean, if you're in general chemistry as a chemistry major, you will have to memorize them. But in introductory chem in high school, a lot of times your professors, your teachers will give you a reference sheet to be able to actually be able to memorize, or at least be able to use this on homework. Maybe for a while they'll eventually wean you off of it. So for us, we will have this for at least for a while. So how does this work? So when we read these charts, it looks a little scary at first, but it's going through all the different geometries that we just talked about. So we went through the first four here. So if I kind of just highlight these and just make this a little thicker just to show. So if we went through the first four, so what this refers to is steric number, which is the same thing as saying electron group. And let's do that in not as thick a letter, so that's readable. So these are electron groups, and that is your steric number. So that would be your first thing you're going to be counting is how many electron groups there are. You need to draw the Lewis structure behind these because you need to know how many lone pairs there are on the central atom. So this is all referring to the geometry around the central atom. Okay, so we need to draw our Lewis structure. And then we are trying to look at the central atom geometry when we are looking at these. So let's practice using this chart. So if I take a few different structures, so let's say if I go back to some of the ones I drew earlier first. So if I had CO2, so what we are doing here is once again, we are counting how many different groups there are. And whether or not you remember from earlier, right, there are two groups on each side of this molecule. So when we see this, right, we have 1, 2. So what we're going to be then doing is going to our chart here. Let's just clean this up a little bit. We're going to be referring to this as our central atom. So the letter E's that are here are your central atom. So you can see there's E's at the beginning of like all these different species here. That's your central. The X's are what's bound to that central atom. So on this last one, we had two electron groups on this. So what we're going to do is we're going to go to the 2. There was no lone pairs around CO2. So what that tells you is that the geometry is linear, right? So we see no lone pairs, only those different groups. So this is our linear geometry for this species. So that's what that tells you. So that tells you that they're 180 degrees apart. This is linear. So let's try a different one. What if I had CO with 2 H's on it? Well, once again, we're looking at carbon as our central atom. And then we're going to be counting the different groups. So we have 1, I don't know why that kind of went away, 1, 2, and 3 here on each side. We're then going to be looking at the different groups. So we have 3. We had 0 lone pairs on this structure. So what that's going to be is going to be trigonal planar is going to be our geometry. So we can redraw this molecule in that orientation. So when we do that, we're going to draw this as trigonal planar. So we have that C double bonded O. We would show the triangular shape behind it. So this illustrates that there's 120 degrees between each of these different groups. Let's try a different one. What if I have water? So water, which is one of the ones that we did in our previous videos quite a bit, is water is the central atom. It's connected to hydrogens on both sides. So how many electron groups does this one have? Well, once again, we're going to count. So we have 1, 2 atoms on both sides. I'm not sure why that's disappearing. So we'll just write it. So we have 1, 2 groups on each side. We have a lone pair, which is 3, and then 4 on all sides. So, however, there might be 4 electron groups, but how many lone pairs are there? So we have 4 electron groups and 2 lone pairs. So when we are doing this, we're going to go back up to our chart. We're going to then be reading across. We'll see we have 4, and we also are referring to having 2 lone pairs. So we're going to go to our 2 lone pairs here. So we're going to come down and across, and we can see that we're going to have a bent geometry for water. So if we draw that now, we can redraw our structure of water. We have our 2 lone pairs on top like little ears, and then each of the hydrogens are pointing downwards. So now we can show that we have less than 109.5 degrees for water. And that's how we would draw that. Let's try a couple others. Let's try 2 more. Let's say if we did CH4, how would we draw that one? So with carbon, there's going to be 4 groups, and there's no lone pairs around the structure. So we can draw it. We can see that there's a hydrogen on all sides, just like this. So what geometry would have 4 different groups? Well, we can see that 4 groups is right on the left-hand side here. And there's no lone pairs on it, so this is going to be tetrahedral is going to be our geometry. So why don't we redraw that as tetrahedral? So this would be C, H, H. We'll draw a wedge, and then a dash to show we have a tetrahedral geometry. Okay, now let's label these other ones real quick. So this was bent. This was trigonal planar. And this was linear up there. So now the last one, let's do another one. Let's say if I gave something a little different. Let's do a slightly harder one. So SF6 is an octet rule violator, which we'll talk about in future videos, meaning that it can expand past a normal octet. So it can make more than the 2 bonds that sulfur normally can do. So if sulfur is a central atom, and I can tell you that, all right, it's going to bond to all the fluorines. So it's going to look like with all the fluorines on all sides. So what geometry would 6 groups be on all sides? So we have 1, 2, 3, 4, 5, 6. How do we do that? Well, we would see that we have 6. There was no lone pairs on it. This one's going to be octahedral. So if we were to draw this one, well, we have it pretty close. We would draw sulfur. Two of them are pointing up and down in the plane. The rest of them are pointing, 2 of them are pointing out, just like so with wedges. And then we would draw 2 of them going away from us as dashes. So this is octahedral. How does these angles work? So with these, it's kind of interesting. So we have 90 degrees on the sides, and then down like the middle, it's like 180 down the middle, or 90 degrees on all parts for the most part. So between what you want to go between. So it's a pretty different geometry. So when you're going through this, this is the basics of how to use the VSEPR chart when you're going through this, and I hope this video helped you to be able to figure out the geometries and to build off of the different Lewis structures. So this is Dr. Dan, and please consider hitting that like and subscribe button for future videos, and I'll see you all later. Bye.